Hi everybody, my name is Vegard. My talk is called Parallelisation in the Linux kernel. So with this kind of talk, it's always difficult to find exactly the right balance and not go either too high level or too low level. I've done my best to try to explain things in what I think is the right level of detail. If you have questions or you feel like there's an explanation missing or something, feel free to ask it anytime in the chat and I'll try to answer it right away. This is a recording, so I should be able to answer things more or less in parallel. So first I'm going to give a little bit of background for the talk and show you where I'm coming from and try to formulate what the problems are and why I think this stuff is interesting, both for me and for you. And then I'm going to take a bit of a deep dive into what happens at the hardware level and the kinds of things that we really need to pay attention to when doing low-level parallel programming. And I'll also go through some specific algorithms that are used in the Linux kernel. Finally, I'm going to give a specific example from the kernel that I think is really nice because it uses a bunch of different techniques and we can see how all of this works out in practice. So I started doing Linux kernel stuff back in 2007, and for the past 8 years, I've been working on Ksplice at Oracle. Ksplice is a service that provides security updates for the kernel and that you can apply to your running machine without having to reboot. I'm not going to go into the technical details of that here, but if you're interested, there is a white paper on our website that explains how it's done. So a lot of this work is looking at kernel patches and figuring out what's exploitable or what's security relevant and what's exploitable and how to make it safe for hot patching and preferably also without sacrificing performance. So there's a healthy mix of security, C programming, and kind of low-level machine stuff. One of the things that I really love about this work is that I get to see a lot of different kernel code. So earlier this year, we had a GPU driver bug where we had to fix the context switching code that runs on the GPU. So it's not even really the kernel code, and I had to learn a lot about how that particular driver works, down to allocating command buffers and like setting individual GPU registers. So that was really interesting. And I do have an interest in graphics programming as well, so it was kind of fun to see the other side of that. So why the Linux kernel and why should you care? The answer is that I think the Linux kernel is quite similar to handmade projects in many respects. First of all, it's low level, basically as low level as you can get for a C program. And related to this, it's also completely self-contained. It doesn't link with any external libraries. There are some cases where code has been pulled in from other projects, but that's limited to like small algorithms like CRC calculations or cryptographic algorithms, that kind of stuff. And kernel developers care a lot about performance and minimizing bloat. And as more of a general point, I think there's a lot to learn from the Linux kernel. Like it has a lot of code, it's doing a lot of different things, it has a lot of interesting algorithms in it. So to me, it's just really interesting as a more of a repository of general programming tricks and ideas. And that's not to say that the Linux kernel is perfect, far from it, and I know that because I've seen my share of bad kernel code. But you'll find that in any large code base, right? So I mentioned that kernel developers care a lot about performance. And part of this is also about scalability. And the Linux kernel really wants to scale down to like tiny embedded devices. I'm not sure if smartphones count, but in any case, Android runs on Linux and you can we put our phones in our pockets, so it's obviously suitable for running on something like that. And it also scales up all the way to massive supercomputers. So this is an example of that. And this commit is from 2013, and it increases the maximum supported number of CPUs to 8,192. And if you read a bit more, it says, the current value of 4096 isn't very silly any longer, as there are actual SGI machines that approach 6096 CPUs. And this was from 2013. As an actual example of this, here's a photo taken in 2016 by a friend of mine. This is a supercomputer at SGI, and it has 6,144 cores. And this thing runs Linux. It appears to the kernel and to user space as a single machine with a single physical memory address space. And just for reference, as far as I could find, Windows has a max limit of 256 cores. And there are different conclusions you could draw from that. What I really want to highlight is the fact that Linux does support it, and when you write kernel code, that's something that you typically do need to keep in mind. Especially if you're working on core structures like memory management or process management, as opposed to maybe like a specific driver or something, then being able to scale up to this level is absolutely something that you need to take into account. So one of the main problems with writing software for so many cores is that you need to access, if you need to access a shared resource, then you may end up serializing the execution of all your cores. And this obviously depends on your exact problem, but if you use one of the main two locking mechanisms, spinlocks and mutexes, then performance will typically get worse as you add more cores. And by worse, I mean you have diminishing returns, right? In the sense that at a certain point, adding more cores won't actually make your program get more work done. If you have two cores doing the same thing, here in this example, taking a spinlock and then accessing a shared resource and then doing some independent work without the lock held, then you will end up with kind of alternating between who has the lock and who doesn't, but they're still both doing useful work most of the time. And if you have the same kind of workload, just with 4 cores instead of 2, you see that more time is spent just waiting for access to the shared resource. And this is just wasted time. Like, nothing actually gets done there. And if you're using a sleeping mutex, then you can potentially switch tasks and maybe do something else until the lock becomes available. But switching tasks is really expensive, as you're not just swapping out, the CPU registers. You're also blowing away your whole cache. In practice, it won't look exactly like this diagram. You'll have more random intervals and stuff, but the problem is still there, right? Having to wait for a lock to be free will get worse as you have more contention. And if you have more cores doing exactly the same thing, then you will have more contention. So one analogy that I heard for locking goes like this. You see the bathroom as a shared resource because only one person can go there at a time. So when you enter, you lock the door, and anybody else who wants to get in has to wait. And when you leave, the next person can enter. And I think this is a good analogy for several reasons. People don't really spend a lot of the total time of their day in the bathroom. Your bathroom trips are going to be short compared to the 24 hours of the day, right? And you can typically get away with having a single bathroom for a household of 2 to 4 people without running into too much trouble. You may occasionally run into a situation where people have to go at the same time and you have to wait. But we can deal with that because you don't have to wait too long. Now imagine that you had to share a single bathroom between, 32, 64, or 256 people. And it doesn't really matter how quick your bathroom trips are because the queues outside that bathroom are going to be long. And now imagine the household with 6,000 people in it. that's just not going to work. Like, the math is simple. If you have a workload with a shared resource and you use locking, this design is not going to scale up to an arbitrary number of cores. That said, there are some things we can do. There are tricks we can use to make things work anyway. Mostly by kind of reducing the constant factor overhead of holding a lock. For example, by reducing the time that you spend holding locks. And another possibility could be to improve the implementation of the lock itself. So I want to give a real-world example that kind of guides what I'll talk about next. And this example is often quoted as Linux kernel developers' favorite benchmarks, and it's compiling the kernel. So actually, for me, it's not just a benchmark, because we do a lot of kernel builds when we build ksplice updates. And we use these 128 core machines to do that. So instead of waiting an hour for a kernel build to finish, we pass -J 64 or -J 128 or something like that, and it takes a few minutes instead. But yeah, for my example, I've used my laptop with 4 cores and just done a default configuration build. So it's nothing like a full distro build with all the modules for all the weird, USB serial drivers or something. My point here is that although a kernel build is fairly parallel, I mean, the whole kernel source tree and the resulting object files fit in the page cache, so it's not really I/O bound. Compiling the C code is mostly CPU bound, so it should parallelize really well. Like, there's no dependency between 2 separate C files, so in theory, you should be able to run them completely in parallel and have no overhead. What you do need to be careful about, though, are the shared resources. And in this case, the top system calls done by the whole build process are like open, read, close, and fstat. So clearly, there's a lot of file system access going on. And that's probably not a big surprise. But there is only one file system, and that it's a shared resource. It's shared between all the CPUs and all the processes. So you really need your file system to support different operations running in parallel without blocking anything else. You can't just take an exclusive lock every time you access the file system, because that would completely kill the performance of a large system. And in fact, the more CPUs you have, the worse the problem becomes, because you have more contention. And we're going to get back to this example later, and we're going to look at how the kernel does pathname resolution in a scalable way. Before that, let's talk a bit about cache. So in practice, on most modern platforms, I think at least on x86, the cache lines are split up into chunks of 64 bytes called cache lines. This means that if you access any byte in a cache line, you're going to be making a 64-byte transfer of memory from RAM into your CPU's local cache. And cache lines are useful because they provide you with fast access to the rest of those 64 bytes as well, which is something that programs very often do. And most people probably think of cache in terms of how you structure your data and what your single-threaded performance is going to be like. But I think a lot of people underestimate how big of a role the caches and the cache coherency protocol has when it comes to performance in parallel programming. When you have a multi-core system, one important thing to remember is that each core has at least one local cache that it can access really fast, and then the other cache levels may be shared between cores. And there is this cache coherency protocol called MESI that's very widely used, and it basically says that only one core can have exclusive write access to any given cache line. So if 2 cores want to write to any part of the same cache line, this would cause the cache line to get written back by the core that currently owns it, and then read back by the core that's requesting write access. So as soon as you have multiple cores writing to the same cache line, you're adding a lot of bus traffic just moving the cache line from one core to another. And when a cache line moves back and forth between different cores and never staying in one place, that's called cache line bouncing. And in most cases, that's really expensive and probably completely unnecessary. And one thing that can cause this kind of cache line bouncing is false sharing. And this can be an issue of putting two or more pieces of data inside the same cache line and then accessing them from different cores. Even though the two pieces of data are completely unrelated, the simple fact that they're in the same cache line means that the data has to bounce back and forth. This can be an easy trap to fall in if you use struct of array, like SOA representations for your data, and each core only accesses some of the elements. So for example, it's always a bit of a red flag if you see an array of something that's smaller than a cache line, and then you give each thread or each core access to one element of that array. And in that case, it may actually be better to add some padding by hand to ensure that each value ends up in its own cache line. So in this specific example, something like 95% of the space in the struct is kind of wasted on the padding, but it will make the program much more efficient because you're not constantly moving the one cache line around between the 16 cores. Instead, we have 16 cache lines and they all just stay at the one core where they're actually used. An example of something you should probably never do is to have an array of locks. Having two or more locks in a single cache line is also a pretty big red flag. It's typically better to put your lock together with the data that's being protected if you can. There are also some other sources of cache line bouncing, but we can get back to that later. So normally when you do things like add one to a variable, this is done with a single instruction. But even if it's a single instruction, there are still two memory operations happening. The CPU first has to read the current value, then increment it, and then write the new value back. So if you have multiple threads doing this in parallel, it's quite possible that two CPUs will read the same initial value, do the same computation, and then write the same result back. Which means that even if you incremented the variable 1,000,000 times, the final value can be way lower than that. Atomic operations basically ensure that nothing else can access the same variable between reading the value and writing back the result. So on x86, that just means adding a lock prefix to your instruction. On x86 and probably most modern architectures, aligned loads and stores are always atomic. So if you're writing to the same 64-bit memory location from two threads, there's no way that you can ever end up reading or writing, say, the upper 32 bits from one core and the lower 32 bits from another core. You'll always see one value or the other, not some kind of mixture between them. And it's tempting to think that because an operation is atomic, it kind of always has the right value. But the truth is that atomic operations are just like other memory accesses, and you still need barriers if you rely on a specific ordering. So here, for example, we're changing the value x, then we're changing the value y. But it's quite possible that another CPU will see the new value of y and the old value of x. So the correct way to think about it is that it's just the one single operation that's atomic. The atomicity does not extend to any other memory accesses. And atomic operations are used to implement things like locking. And I'd like to do a spinlock example. Spinlocks are one of those things that look really simple on the surface, but can actually be made incredibly much better by thinking about what's actually going on at the level of the hardware and the cache. So this is like the simplest kind of spinlock you can have. This CMP XCHG means compare and exchange. So this call here basically compares the value of the variable locked to 0. And if it's 0, then it atomically sets the variable to 1. And then it returns the old value. And honestly, I always forget what the arguments are to this function and what it returns. But the way to read this is basically what the comment says. The loop keeps going until we succeed in replacing 0 by 1. And if there are several CPUs trying to acquire the lock, this will only happen for one of them, since the comparison and the replacement is done atomically. So once the value has changed from 0 to 1, no other CPU will be able to leave the loop until the value goes back to 0. And if you really want to know what the exact semantics of this compare and exchange is, I'll show the non-atomic version here, but this is still kind of hard to read on the fly, so this is more for if you want to go back and look at the slides later. The very first thing we'll want to do to optimize the spinlock is to insert a hint to the CPU that this is a busy loop. And as far as I know, this only really does something if you're using hyperthreading or and it allows the CPU to spend more time or resources on the other hyperthread instead of just burning cycles pounding on this lock. A bigger problem with this loop is that the atomic compare and exchange actually tries to get exclusive access to the cache line. It wants to write to it, right? And that means transferring the whole cache line to our local core. And remember that the CPU itself has no idea that this is a lock. And the CPU, which is holding the lock, most likely still wants to access that same cache line that the lock is in. So any other CPU that tries to come in and grab the lock will actually transfer the cache line to itself, only to see that the lock is already held. And now if you have more than one CPU doing this, you'll see that the cache line is going to be bouncing back and forth like crazy between the various local caches of the CPUs that are spinning on this lock. So what we can do instead is to just read the value first using a plain read. And I said before that on x86 there's no way that an aligned read can be non-atomic. In the Linux kernel, we still have this atomic read helper, which compiles down to a plain read on x86. And here the ownership of the cache line is not going to change by doing the plain read. And so you can prevent a bunch of useless bus activity until the lock is actually available. And that can be like a real significant optimization for a contended lock. But the Linux kernel actually doesn't do this. It splits the code into a fast path and a slow path. And the fast path assumes that there is no contention, which means we expect to get the lock on the first try. And if we don't get the lock on the first try, then we go take the slow path. And the kernel currently uses something called queued spinlocks, and they were introduced in this commit. And it says, this queued spinlock is especially suited to NUMA machines with a large number of cores, as the chance of spinlock contention is much higher in those machines. The cost of contention is also higher because of slower internode memory traffic. So this is a prime example that the code is explicitly written for NUMA machines with a huge number of cores, and they explicitly care a lot about contention and cache line bouncing. So just to talk a little bit about NUMA, for computers that have a lot of CPUs, you typically split them into sockets. And this is actually the number of physical sockets on the motherboard. So each socket has access to its own memory and its own cache and all of that. But each socket also has a connection to other sockets, which will allow it to access all the memory in the machine. However, it's much slower to access memory outside of your own socket. So that's why the commit is talking about the cost of contention. Because now you're not just moving the cache line from one cache to another, you may actually be moving it from one RAM chip to another. And then now we begin to see how costly it can be to request access to something that you can't really use anyway. To go back to the queued spinlocks, what makes them so great for NUMA machines, and probably also smaller machines, is that they avoid what's called global spinning. And global spinning is when all the threads are spinning on the same global address. It may be hard to imagine a spinlock where you don't do this, and and you still end up with a proper lock, but that's very possible. So with queued spin locks, you actually spin on a local per CPU variable, and then when the core that's holding the lock releases it, it notifies only the next waiting thread that it now has the lock. And since you're spinning on a local variable, there's no traffic on the memory bus except when you do the handover to the next thread. I'm not going to go into all the details of the implementation here, but fundamentally, instead of having the lock only be either 0 or 1, you also encode an address in the upper bits of the lock, so that when the lock is held, that address points to the last element of a linked list, which is a queue of CPUs waiting to take the lock. The head of the list is the owner of the lock, the current owner. So you can imagine that every time a new CPU wants to take the lock, it swaps out the value of the global variable with a pointer to their own per CPU value. And then since they did a swap, an atomic swap, they also get the old tail pointer for that list. And they can now update that tail to point to their own local value. So when the lock owner wants to release the lock, it just follows the pointer that it has in its local value, which points to the next CPU that's waiting to take the lock. And all of this is a little bit tricky, but it works out, and that really helps to reduce bus traffic. And there is currently a new Spinlock implementation under review, which improves support for NUMA systems even more by basically trying to hand the lock over to another core on the same socket, because that's much cheaper than handing it over to a core on a different socket. One of the amazing things about this particular implementation is that they managed to keep the size of the Spinlock itself at only 4 bytes, meaning it's essentially a drop-in replacement, and it doesn't affect existing kernel structs at all. And if you're interested, I highly recommend this paper, as they explain things really well. And just to be completely transparent, this research does come from Oracle Labs, and I've not been involved in any of this. I'm just including it here because I think it's really cool. There is also a variant of Spinlocks called reader-writer Spinlocks. And this idea plays on the observation that you could let multiple readers all have access to the same shared resource, as long as there are no writers making modifications concurrently. So the benefit is obviously that you now have parallelized the readers. And this seems like a really good idea, but in practice, it turns out that there is a big problem with writer starvation. Basically, you can end up in a situation where there are new readers coming in all the time, and basically they're completely blocking any writers from getting their work done. You could imagine ways to fix that, for example, by only letting a limited number of readers in at a time, or maybe you have some kind of time limit after which readers are forced to wait. But then that's also kind of weird because now you're blocking the readers when it seems like they could have had access. So it's something that you could use, but there may also be even better ways. And the best thing that we can do is to get rid of locks altogether. And the technique that's being used more and more in the kernel is called RCU, which stands for read copy update. And what it gives you is essentially wait-free read access to various data structures. And by wait-free, I mean that you don't need to take any locks and you don't need to hang around just to read the data. Even if there is a writer modifying the data structure, you can go ahead and read it at any time. This typically needs a little bit of careful pointer manipulation just to ensure that the reader always sees something that makes sense. And writers, on the other hand, they do need exclusive access, so they need to either be able to make changes with a single atomic instruction, or they need some other way to ensure that no other writers can access the data structure at the same time. And that could be, for example, a spin lock. But that lock's only taken if you're actually modifying the thing. So to give a concrete example of an RCU data structure, I'll use what's arguably the most frequently used one in the kernel, which is RCU linked lists. And the read-only operations here are things like traversing the list, checking if the list is empty, or getting the last element of the list. And write operations are things like adding an element or removing an element. And the Linux kernel really likes to use doubly linked circular intrusive lists a lot. Doubly linked because it means you can remove an element in constant time. You just so you have the pointer to the element you want to remove, and from that you know the prev and next pointers, and you just update those nodes to point to each other. It's circular because it simplifies the implementation a little bit. You don't need to care about the sentinel values like the nulls at the end or something. And finally, it's intrusive because it means there's no separate allocation for the list nodes and the things that you put into the list, which I think is just common sense. So for RCU, if you want to traverse the list, you can do this at any time. The only thing you need to ensure is that as you go from one node to another, the next pointer is always valid. And the problem is that you frequently take stuff off a list because you're about to delete that object. And if you delete it, the pointer to it won't be valid anymore. So how does a writer that just removed an element signal to the reader who just read that pointer and is about to access it that the node is gone? Or how does the writer prevent the reader from seeing one of those pointers? So the trick here is actually to never free the element you removed until all the readers are done with it. So the writer who just removed the element wants to free it, but that free needs to be delayed a little bit until all the readers are done with it. You might think that involves some reference counting or something, but there is a different way to do it, which is cheaper than that. So if the reader has a pointer to something and wants to ensure that it doesn't go away without using reference counters or anything like that, what we can do is this. The reader has to disable preemption. And put very simply, this means that the current task will keep running until preemption is turned back on. So even if a timer interrupt comes in, it won't be able to context switch to a new task. So we're kind of locking the task to the CPU for a short amount of time. And that's almost completely free. We're just bumping a CPU local variable when disabling preemption and then bumping it back when we're done. And this has the effect that when the scheduler does kick in sometime down the line, we know for a fact that the reader is done with the pointer from the RCU protected list, because otherwise the scheduler wouldn't be running in the first place. And on the writer side, we need to keep track of what tasks may still be running and decide when it's safe to free the list element. And the RCU API provides two ways to do this. The first is synchronize RCU, which actually stops and waits until all the readers have gone through a grace period. And this can actually be quite costly to figure out. But it still gives you better scalability because the delay is only on the writer side and it only delays the one writer. And the second method is call RCU, and that does the function call for you, but only when all the readers are done. So call RCU doesn't block the writer, but it does require a little bit of memory somewhere to store the callback and the fact that we would like to call it at some later point. So for RCU linked lists, you need to disable preemption when traversing it. You need to lock the list with a spinlock during modification, and you need to delay freeing using the RCU API. And of course, the RCU list implementation itself needs to be really careful about reading and writing pointers atomically and ordering memory accesses so that you don't, for example, expose an uninitialized element before you add it to the list. And actually with RCU, you can't really traverse lists in reverse because only the next pointers are guaranteed to be updated in the correct order. And it kind of makes sense because you have to choose whether to update the prev or next pointer first if the CPU doesn't have an atomic instruction that can update two pointers at once. And next, I want to talk a bit about sequence locks. And I think these are pretty funny. They're a bit simpler than RCU. Like RCU, they're really good when you have lots of readers and very little writing or modifications going on. But unlike RCU, some of the cost of writing is put on the readers. So I've dared to put a code example here. Hopefully it won't be too difficult to follow. The first thing to note is how to declare a lock. You can have a global variable like this, or you can put it in a struct, whatever you want. On the reader side, you're basically reading a sequence number. Then you do some computation with the data that you're interested in, with the shared data. And then at the end, you check whether the sequence number is still the same as it was before you started. So if it's the same, then great, the data wasn't modified and you can go ahead and use the result. And if it's not the same, that means somebody did something to the data and we don't really know if what we did is valid anymore. And the common way to handle that is just go back and try to do the same thing again. Of course, you could also give up and return an error, or you could fall back to taking a real lock, like a spinlock or a mutex. And on the writer side, like with RCU, you have to protect multiple writers from each other. So this the sequence lock embeds a spinlock that gets taken by the writers, and then when you lock and unlock, you also bump the sequence counter atomically to kind of notify the readers that the data they got could be stale or inconsistent. And that's pretty much all there is to sequence locks. Like, the reader is very simple and very cheap until the moment you actually have a writer. But then when you do have a writer, it can be very expensive if you keep looping around and never getting the result you're hoping for. So there's a real possibility here for starving the readers, which is why you may want to fall back to a proper lock when there's contention. So to return to our example with the file name lookups that I talked about way back, on Linux, the file system is organized as a single hierarchy called a VFS, for short for a virtual file system. So when you boot, you start out having an empty VFS, so it's just this empty directory, and that's where you mount your root file system. And you can then mount different partitions or different types of file systems at any subdirectory in the VFS. So it's not like on Windows where you have the drive letter and then you know that anything following that is a path on that drive. In any given directory, you have a list of directory entries. So all of these here in red are directory entries. They're basically file names, and they can refer to files or directories or special files, device files. In order to make a path traversal fast, directory entries are cached in a big shared hash table called the directory entry cache, or dcache for short. And this hierarchy gets loaded into memory from disk as you access them, and once they're loaded, you can traverse path names completely in memory. And of course, if the machine is low on memory, then they can also get unloaded. So to start walking down this path, you start out with a parent directory being either the current working directory or if the path name starts with a slash, then it's an absolute path and you start at the VFS root. So at each step, you will have a parent pointer, which points to some directory entry object in memory. And you'll also have the name of the next component that you're trying to look up, and that's a string. So you hash these two together, and you use the resulting number as an index into the directory entry hash table. And as you descend down the path, you repeat this process of looking up the next component and continuing the search. You just repeat it for every component. And that all sounds pretty easy, but it's actually a lot more complicated than that. So first of all, permissions on Linux are tied to files and not to the directory entries, which means you need to find the inode that the directory entry refers to, and you have to load it and check the permissions on it. You can also have symbolic links, which redirect you to a different file. So you need to read the contents of the symlink, which involves going to the inode or to the underlying file system. And the contents of a symlink is a path of its own. So it can be either absolute or it can be relative to the current position. So if it's absolute, then you throw away your current position and you replace it again by the VFS root. And if it's a relative path, then you need to walk each of those entries in the symlink. And when you're done with that, if you found the target and it's a directory, then you have to continue walking the components of your original path. And symlinks can be nested as well, so you may have to repeat this process several times. And then, since other file systems can be mounted anywhere in the VFS, this means you may start out traversing a path on one file system and then cross into a different one and continue the traversal there. And of course, the problem with all of this is that the file system is global, so you need to guard against other processes making changes while we're doing the traversal. And in particular, some of the problems that may occur could be related to files getting renamed, moved, deleted, or maybe the whole file system got unmounted while we were walking the path. And so the bottom line here is that there are a lot of different data structures involved. We need to be very careful about how we access things and make sure that we get a consistent view of the file system, and also that we don't accidentally, follow a stale pointer and crash or something. So you can hopefully see where I'm going with this. We want path name lookups to be fast, but also correct. So what the kernel does is it has two different mechanisms for path lookup. And the first one is kind of what you would expect to see as a naive solution. It takes a bunch of locks, it bumps all the right reference counters, it's pretty slow, but it's correct. And then it also has a fast version that uses RCU and sequence locks and very carefully avoids waiting for any writers or making any modifications to the shared data at all. And if you remember the bits about the cache and the MESI protocol, then this is really good because we're not invalidating cache lines on other CPUs or other sockets. We're not doing any of that expensive stuff. So why wouldn't you always use the fast version? Well, sometimes you can't, right? If there is a concurrent modification to any of the things you need to read during the traversal, you may potentially have to go all the way back and redo it from the beginning. So instead of potentially stalling forever, what Linux does is it tries to do the fast version first, then it falls back to the slow but safe version if that fails. And one cool thing about the sequence locks is that you can validate it as many times as you want as you descend down the path, and it won't actually be expensive unless something's actually changed. But in that case, it will be expensive to recover anyway, like if something's changed, and so you don't really lose anything from doing it. Alright, so that actually concludes most of the talk. I'd like to finish by just offering a few final thoughts. If you do massively parallel programming, you need to get used to thinking in terms of cache lines and the cache hierarchy. And that holds whether you're working on the locking primitives themselves or you're writing something that uses those primitives. And I think this is where the handmade attitude really comes in handy, since you need to know how things work on the layers below if you're going to be using any of these techniques. Another thing that we see with RCU and spinlocks and sequence locks is that they're all optimized to go fast in the common case and then fall back on something that's maybe slower but always gives you the correct result. I'm not sure how conscious people are of this as a general programming pattern, and I certainly didn't realize for a long time how powerful it could be. But this is really the backbone of many of these parallel algorithms. I would also encourage people to look at different code bases, to look at different coding styles and different algorithms. And I think we often kind of get caught up in local paradigms or kind of narrow mindsets. Like some people wouldn't touch a linked list with a 10-foot pole. And I've also seen people who think reference counting is the worst thing in the world, when actually that's one of those things that can work really well in specific situations. So, as always, beware of monoculture and thinking that something is always bad just because somebody said so. And I know that many of you probably don't like Linux that much as an operating system, and that's fine. But the truth of the matter is that the Linux kernel is where you will find a lot of state-of-the-art algorithms when it comes to concurrency, parallelism, and scaling to thousands of CPUs. And the best part is that anybody can go look at it and learn from it. And there's even some pretty good documentation out there. I honestly encourage everybody who's interested to go have a look at the code and the documentation. It's all out there. So I think we have about 10 minutes to do questions, and I'll be answering in the chat. If you think of a question after that or after the conference is over, don't hesitate to get in touch by email or whatever. I'm also in the Handmade Discord. I'd love to hear what you thought about the talk, or if you're interested in Linux kernel development or in Ksplice, I'm also happy to answer questions about those. So please reach out, and thank you.